This is the projectile motion lesson part 2, and we will again emphasize what is projectile motion and how to approach a projectile motion question. So projectile motion is a combination of two motion. One is uniform motion and the other one is non-uniform motion, in a difference with the relative motion that both of them were uniform. The uniform motion is happening in projectile motion on the horizontal axis, while the non-uniform motion is happening on the vertical axis. To have a uniform motion means that acceleration is equal to 0, velocity is constant, and the displacement is calculated with the formula v times t. And to have a non-uniform motion, then that means that the acceleration is not equal to 0, maybe positive, maybe negative. The velocity is changing, and actually the rate of change of the velocity will be the acceleration. And the way that we solve for the displacement is using kinematics equations. As I have mentioned, even when we did kinematics equation, this is, as we have mentioned when we did kinematics equation, the one that is mostly used is VIT plus 1/2 AT squared. Considering this as the bone of the projectile motion, the way that we approach and solve any projectile motion question is by writing down the horizontal and vertical. So writing down what is happening in the horizontal and what is happening in the vertical. So in the horizontal, as we said, we have uniform motion. On the vertical, we have non-uniform motion. This means that on the horizontal, acceleration is equal to 0, not A. Acceleration is equal to 0. And in the vertical, acceleration will be the acceleration due to gravity. And since we are assuming that most of the cases, the object is thrown at the surface, near the surface of the Earth, the acceleration due to gravity will be 9.81 meters per second square going down, which in terms of the positive and negative, it is, since it is going down, it's negative 9.81 meters per second square. Now, if this is happening, the projectile happening to be in, let's say, moon, then you will write the acceleration due to gravity of moon. And if it is happening to happen in, I don't know, in another planet, then you will use that value. So acceleration for both horizontal and vertical is stated. And then we have the horizontal velocity, since it is constant, we are dealing with a uniform motion, will be whatever is the horizontal component of the initial velocity. And the velocity on the vertical axis will be v initial vertical minus 9.81 t, following this equation. So this will be for the second physical quantity that we discuss in terms of the motion. So the first is acceleration, then velocity, and the third one is displacement. And since we are dealing with a uniform motion in the horizontal, that means that the displacement will be whatever is the velocity times time. And in the y-axis will be the vertical component of the initial velocity times time minus 1/2 times 9.81 t squared, and 1/2 times 9.81, it's safe to say it's 4.91 t squared. So with this discussion that we have in terms of the projectile motion, we have created 6 equations: 1, 2, 3, 4, 5, and 6. What we will do today is that we will see what is happening with those equations in terms of graphing. So we'll discuss them from the horizontal and from the vertical component. The very first thing that we will see in terms of the acceleration in the horizontal and time graph. So in the horizontal, we have a 0 acceleration because we have a uniform motion. So during the whole time, what we have is the acceleration is equal to 0. But if we move to the acceleration in the vertical axis versus time, the acceleration will be negative g. So a negative g, which near the surface of the Earth is negative 9.81 meters per second squared. So the graph of the acceleration will be like this. Understand? Do you have any questions? So the acceleration in the horizontal is 0. We are dealing with a uniform motion. And the acceleration in the vertical is a negative acceleration due to gravity. So this is why the graph looks like this. In the horizontal, the velocity will be a straight line, and that will intersect the vertical axis into the value of the horizontal component of the initial. And this even makes sense when we talk about the graphing, that the slope of the velocity times graph gives us the acceleration time graph. So the slope of a horizontal line is equal to 0. That means the acceleration in the horizontal axis is equal to 0. And when we are discussing and talking about the velocity in the vertical axis, will be a line that is falling down, and the y-intercept of it will be equals to the vertical component of the initial velocity, and the slope will be negative, or acceleration due to gravity, which, since we are assuming that is at the surface of the Earth, is negative 9.81, and the x-intercept will be the point where the maximum is reached, which means that the velocity at that point is equal to 0. And we discussed this and did it mathematically yesterday, how to calculate the time that the maximum is reached. Okay. So now let's move to the displacement time graph. So displacement in the horizontal, which for the simplicity we say, just say x will be versus time will be something like going up. And now we know that the area of this graph here will be where what we calculate to construct the displacement time graph, and the slope of this graph will give us the value, or the way that we calculate the horizontal component of the or the velocity in the horizontal axis. And for the displacement on the vertical versus time graph, what we will have a maximum that is reached here, and then it is falling down. Okay, so and again, as I have mentioned when we did graphing, this will make way more sense when you learn about calculus. But what this is the instantaneous slope of the displacement time graph will give us the graph of the velocity time. So this brings us into a question that you even had in your kinematics equation quiz, where you were asked to figure out, to find what is the acceleration at the top. What is the acceleration of the motion at the top, where the maximum is reached? If you have a projectile or an object that is thrown at a certain velocity, up, down, whatever is it happening, when you are near the surface of the Earth, the acceleration is constant, and it is the acceleration due to gravity, which is 9.81. And if you are in another planet, then will be whatever is the acceleration due to gravity of that planet. So if I will draw a projectile motion, like the path, the trajectory of a projectile motion that is thrown with an initial velocity that goes like this. So the path or the trajectory, assuming that what is happening is no air resistant and no wind. And this is a ground-to-ground situation, but the same thing is for the throwing it from a cliff. The maximum, when the maximum is reached, the acceleration is 9.81. And the acceleration is always, at any point during the motion, the acceleration is always going down, equals to the acceleration due to gravity. That being at the moment that you are throwing it, in between here, at the maximum, or when you are hitting the ground. Acceleration is not changing. It is equal to the acceleration due to gravity. And since we are dealing with the surface of the Earth, will be 9.81 meters per second squared. Now, let's do a question that is ground to ground again, that is dealing, it's kind of similar to what we did yesterday. So if you feel that you know this stuff, you can go or stay, and then you will see the steps emphasized. Let's suppose that we have a situation when an object is thrown with an initial velocity of, well, I will say 120 meters per second at 25 degrees with the horizontal. This is what you will usually see in the projectile. You may say that it's 25 degrees north of east or whatever. So as a step, first step that we do when we are dealing with projectile motion is to find the horizontal and a vertical component of the initial velocity. What does that mean? finding the horizontal and vertical component of a vector. So you have a vector that is with a magnitude of 120, and the angle that is creating with the horizontal is 25 degrees. So then what you will do is you will create the right angle triangle that includes the given angle. Whatever is on the horizontal will be the horizontal component of the, in our case, initial velocity. And whatever is on the vertical will be the vertical component of, in our case, the initial velocity. So the horizontal component of the initial velocity will be 120 times cosine 25 degrees. And in your calculator, 120 times cosine 25 degrees will be 108.8 meters per second. And the vertical component will be 120 times sine 25 degrees. And using your calculator, and again making sure that the mode is on degrees, this will be 50.7 meters per second. Using those two values, we will construct, I would say, the table that we discussed before. And as I mentioned even yesterday, this will help you to get into the habit that you write horizontal and vertical, uniform, non-uniform. Acceleration is equal to 0. Acceleration, assuming that we are dealing with throwing an object at the surface of the Earth, is negative 9.81. The velocity in the horizontal will be whatever is the horizontal component of the initial velocity, 108.8. You can even say 109. I will be in peace with that. The vertical component will be 50.7 minus 9.81 t. And the displacement in the horizontal will be 108.8 times time. And on the vertical will be 50.7 t minus 4.91 t squared. So now we have equation 1, 2, 3, 4, and 5 and 6. And then what we are asking here is the first one, where, at what time the maximum is reached. So which equation are we using to solve for that? Answers here on the chat. So someone here is saying on the chat that we may use equation 6. Yes, you may. What you will do if you are using equation 6 will be 50.7 t minus 4.91 t squared is equal to 0, because the equation will be 0. So factoring out t, you will have 50.7 minus 4.91 t is equal to 0. And this using zero product property rule, which is a math thing, you can find that t is equal to 0 or t is equal to 50.7 over 4.91. This is what you will do if you are using equation 6. But another answer here is equation 4, and that is the easiest. So you may do this or 4. So when we are using equation 4, what we are saying, I will use a different color. What we are saying is that the velocity at the maximum is equal to 0. So velocity in the vertical axis is equal to 0 at the maximum. So then we take the equation of 4, and then we substitute 0 is equal to 50.7 minus 9.81. 81 t is equal to 0. Why is this not? So when we are using equation 6, what we are doing is we are finding the total time. And when we are using equation 4, then we are finding the time at the maximum. Because see, what we are doing here is in the y and x-axis, we are finding the time that the object crossed the x-axis. So this is t equals 0, and this will be t equal to 50.7 over 4.91. When we are using equation 4, we are finding that moment here where the velocity in the vertical axis is equal to 0. This time here, which is actually in the middle of those two times. Make sense, guys? Okay. After we find the T max or T total, so total time, which you can find either as we did using equation 6 or doubling the maximum time, and this is true only for the ground to ground. Then let's find the maximum height and a range. When we are finding maximum height, which equation are we using? 1, 2, 3, 4, 5, or 6? Answers here. Yes, we are using equation 6. And what are we substituting for time? T max or T total? T max, good. So maximum height will be 50.7 times T max, whatever was T max, minus 4.91 T max to the power of 2. And then you will have a maximum height. What are we, when we are finding the range, which equation are we using? 1, 2, 3, 4, 5, or 6? And what is the time that we are substituting here? T max or T total? T total, good. So this will be x equals to 108.8 times whatever is T total. And that will give you the value of the range. Okay, so